Settle into the sleepy mind channel. Today we will explore how animals survive the deep cold. If you like videos like these, feel free to like and subscribe. More videos are posted weekly. You can also browse the full playlist for more calm and engaging topics, all designed to help you relax as you listen. A small wood frog rests beneath a thin layer of ice as winter settles in. Its body is stiff and motionless, and as the temperature drops, ice begins to form within its tissues. Its heart no longer beats in the usual way, and its breathing has stopped. To most forms of life, this would mark the end of activity. Yet for this frog, it is part of a process that allows it to survive the cold. As the environment continues to freeze, the frog does not resist these changes. Instead, its body responds by adjusting how it functions at a fundamental level. Water inside its tissues begins to freeze in a controlled way, while internal compounds help protect its cells from damage. This process allows the frog to remain stable even as conditions become extreme. It is not active, but it is not lost. It exists in a state that allows survival through the harshest part of winter. Nearby, other animals respond to the same cold in very different ways. A bear moves into a den and begins to reduce its activity, relying on fat stored within its body to sustain it. A ground squirrel settles deep into its burrow, lowering its body temperature until it nearly matches the surrounding soil. A bat hangs motionless inside a cave, where the air remains cold and steady. Each of these animals faces the same environment, yet each uses a different method to survive it. The challenge they all share is clear. As temperatures fall, food becomes difficult to find, and water may freeze. Movement requires energy, and that energy becomes harder to replace. For the wood frog, remaining still allows it to tolerate freezing conditions. For the bear, reducing activity allows it to conserve energy. For the ground squirrel and the bat, slowing internal systems provides a way to survive without constant feeding. Each response reflects a different balance between the body and the environment. These changes are not sudden. They develop gradually as seasonal conditions shift. As daylight becomes shorter and temperatures begin to fall, animals respond to these signals in ways that prepare them for what is coming. The wood frog begins to produce compounds that will later protect its cells during freezing. The bear increases its food intake, building fat reserves that will support it through months of rest. The ground squirrel gathers energy and prepares its burrow, while the bat seeks out a stable environment within its cave. This preparation is guided by internal biological systems that respond to external conditions. Hormones adjust hunger, metabolism, and activity, ensuring that each animal prepares at the right time. The wood frog does not consciously prepare to freeze, but its body begins to change in response to the environment. The bear does not calculate how much fat it needs, yet it feeds consistently as its body signals the need for energy storage. These processes happen naturally, guided by biological rhythms. As winter takes hold, the shift into survival becomes more noticeable. The bear settles into its den and begins to reduce its movement. Its heart rate slows, and its body relies on stored energy rather than constant feeding. The ground squirrel lowers its metabolism, reducing the amount of energy it uses to maintain essential functions. The bat, hanging quietly in its cave, adjusts its body temperature and breathing to match its lower energy needs. Each system changes in a controlled way, allowing the body to remain stable. The wood frog undergoes a more extreme transformation. As freezing begins, ice forms outside its cells, drawing water away from delicate internal structures. At the same time, protective compounds within its body help prevent damage. Its heart stops beating and its breathing ceases. Yet its cells remain intact, preserved in a way that allows life to continue once conditions improve. This process represents one of the most remarkable adaptations to cold environments. Despite these differences, all of these animals share a common goal. They must conserve energy, maintain stability, and respond to the changing environment with precision. The bear achieves this through controlled rest and stored fat. The ground squirrel does so by lowering its body temperature and metabolism. The bat relies on a stable environment to support its reduced state. The wood frog survives by tolerating freezing itself. Each method reflects a different solution to the same challenge. These strategies show that survival in the cold is not about resisting the environment. It is about adjusting to it. By changing how their bodies function, animals are able to endure conditions that would otherwise prevent life from continuing. The wood frog beneath the ice, the bear within its den, the ground squirrel beneath the soil, and the bat within the cave all demonstrate this principle in different ways. Through these adaptations, animals create a balance between their internal systems and the world around them. They reduce activity, conserve energy, and maintain stability over time. This balance allows them to survive long periods of cold without constant movement or feeding. It is a quiet process, guided by biology and shaped by the environment, that allows life to persist even in the most challenging conditions. As winter approaches, the wood frog begins preparing long before the first layer of ice forms around it. During late autumn, while the ground is still soft and temperatures remain above freezing, the frog remains active for a short period. It moves through its environment, feeding and storing energy within its body. This energy is not used immediately. Instead, it is held in reserve, allowing the frog to survive when food is no longer available. These early changes are part of a gradual process that prepares the frog for the extreme conditions it will later endure. At the same time, other animals begin their own forms of preparation. A bear increases its feeding, consuming large amounts of food to build fat reserves that will sustain it through months of rest. A ground squirrel gathers energy and stores it within its body, while also preparing its burrow as a protected space. A bat seeks out a stable environment within a cave, where conditions will remain consistent throughout the winter. Each of these animals responds to the same environmental signals, but their methods of preparation reflect their specific needs. For the wood frog, preparation involves more than storing energy. As temperatures begin to fall, its body starts to produce compounds that will later protect it during freezing. These compounds build gradually, becoming more concentrated as winter approaches. At the same time, the frog reduces its activity, conserving energy and limiting exposure to unnecessary risk. This shift is controlled and steady, allowing the frog to transition into a state that can tolerate extreme cold. These changes are guided by environmental cues, such as daylight and temperature. As days become shorter, internal systems begin to adjust. Hormones shift to regulate metabolism, energy use, and activity levels. The wood frog does not respond to a single event, but to a series of signals that together indicate the approach of winter. This allows its body to prepare in advance, rather than reacting once conditions have already become severe. Energy storage remains a critical part of this process. The frog stores energy within its body in a form that can be used slowly over time. Unlike a bear, which relies heavily on large fat reserves, the wood frog balances its energy use with its ability to enter a state of suspended activity. This allows it to survive without needing to maintain constant internal function. Its preparation focuses on stability rather than continuous energy use. Other animals demonstrate different versions of this same process. A squirrel gathers food and stores it in multiple locations, ensuring that it can access energy throughout winter. A bear builds a large reserve of fat, allowing it to remain inactive for long periods. A ground squirrel prepares by both storing energy and adjusting its internal systems for deep hibernation. These differences highlight the variety of strategies used to respond to the same environmental challenge. As preparation continues, the behavior of each animal becomes more focused on conservation. The wood frog begins to limit its movement, remaining closer to the ground where it will eventually settle. A bear, after building sufficient reserves, begins to reduce its activity and seek out a den. A ground squirrel spends more time within its burrow, while a bat settles into a stable position within its cave. These changes are gradual, creating a smooth transition into the next phase. The timing of this preparation is essential. If the wood frog does not produce enough protective compounds before freezing begins, it would not be able to survive the formation of ice within its body. If a bear does not build sufficient fat reserves, it would not have the energy needed to sustain itself through hibernation. Each step must occur at the right time, guided by internal systems that respond to environmental signals. As temperatures continue to fall, the wood frog reaches the final stage of preparation. Its body contains the compounds needed to protect its cells. Its energy use has been reduced, and its activity has slowed. It moves into a position beneath leaf litter, where it will remain exposed to freezing conditions. This location does not protect it from the cold, but it provides a stable environment where the freezing process can occur in a controlled way. At this point, the frog is no longer preparing in the same way as other animals. A bear enters its den and begins a state of reduced activity. A ground squirrel moves deeper into its burrow, preparing for a drop in body temperature. A bat settles into a stable environment that supports its low energy state. The wood frog, however, remains in place, ready to undergo a process that involves freezing itself. Despite these differences, the underlying pattern remains consistent. Each animal responds to environmental change by adjusting its internal systems and behavior. Energy is gathered, stored, and conserved. Activity is reduced, and stability is maintained. The wood frog, the bear, the ground squirrel, and the bat all demonstrate different forms of preparation, but each reflects the same need to survive the coming cold. Through this preparation phase, animals show how precisely the body can respond to seasonal change. The wood frog builds the chemical protection it will need. The bear stores energy within its body. The ground squirrel adjusts its metabolism in advance, and the bat selects an environment that supports its survival. Each step is part of a continuous process that allows life to persist, even as conditions become increasingly difficult. By the time winter fully arrives, the wood frog is ready. Its body is prepared to tolerate freezing, its activity has slowed, and its internal systems have adjusted to match the environment. Other animals reach their own forms of readiness, each based on their specific strategy. This preparation ensures that when the cold becomes most severe, the body is already aligned with the conditions it must endure. As winter deepens and temperatures begin to fall below freezing, the wood frog reaches the moment its entire preparation has been leading toward. Resting beneath a layer of leaves, its body is exposed to the cold air above and the frozen ground below. The temperature continues to drop steadily, and as it does, the first signs of freezing begin to appear. Ice starts to form on the surface of the frog's skin, spreading gradually as conditions become more severe. This is not a sudden or chaotic process. It unfolds in a controlled way that allows the frog's body to respond as freezing begins. As ice forms on the outside of the frog's body, internal changes begin almost immediately. Water starts to move away from the cells and into spaces where freezing is less damaging. At the same time, the frog's body increases the concentration of protective compounds within its tissues. These compounds help stabilize the cells and reduce the impact of ice formation. The process is precise, ensuring that freezing occurs in a way that does not disrupt critical structures. This controlled movement of water and protective chemistry allows the frog to enter a state that would otherwise cause severe damage. As freezing continues, the frog's internal activity begins to slow dramatically. Its heart rate decreases until it no longer beats in a continuous rhythm. Breathing, which has already slowed during preparation, comes to a stop. Circulation is no longer active in the way it is during normal conditions. Despite this, the frog's cells remain intact and stable. This state is not one of active life, but it is not the end of function. It is a controlled suspension that allows the frog to endure the cold. While the wood frog undergoes this extreme transition, other animals respond differently to the same drop in temperature. A bear, deep within its den, does not freeze. Instead, it lowers its heart rate and reduces its activity, maintaining a stable internal temperature. A ground squirrel, hidden within its burrow, allows its body temperature to drop significantly, but it avoids freezing by remaining within a controlled range. A bat, hanging in a cave, continues to breathe slowly as its body operates at a reduced level. Each of these animals avoids freezing, while the frog tolerates it directly. The difference between these strategies highlights the unique nature of the frog's adaptation. For a bear, maintaining internal stability is essential. Its body must continue to function at a reduced level without crossing into conditions that would cause damage. For a ground squirrel or a bat, lowering temperature and metabolism provides a way to conserve energy without freezing. The wood frog, however, allows freezing to occur, relying on its internal protections to survive the process. This represents a different approach to the same environmental challenge. As more of the frog's body freezes, the amount of active liquid water within its tissues decreases. Ice forms in controlled areas, while cells remain protected by the compounds produced during preparation. This balance ensures that freezing does not cause physical damage to delicate structures. The frog's body enters a state where biological activity is reduced to a minimum, and most processes are paused. The environment around it remains cold and stable, supporting this condition. At this stage, the frog is completely motionless. There is no visible sign of activity, and its body remains still beneath the ice and snow. This stillness is not a sign of failure. It is the result of a controlled transition into a state that allows survival. The frog's body is no longer using energy in the way it did before. Instead, it has shifted into a condition where energy use is nearly stopped, preserving its internal structures until conditions improve. Other animals maintain a different form of stillness during this time. A ground squirrel remains deep within its burrow, its body temperature low but stable. Its heart beats slowly, and its breathing is minimal. A bat remains suspended in its cave, relying on the consistent environment to support its low energy state. A bear rests within its den, its body using stored fat to maintain essential functions. Each of these animals remains alive through controlled reduction, while the frog exists in a state of suspended activity. The freezing process does not continue indefinitely. Once the frog's body reaches a stable frozen state, the changes slow and eventually stop. Ice remains present within its tissues, and the protective compounds continue to stabilize its cells. The environment plays an important role during this period. Consistent cold temperatures prevent repeated freezing and thawing, which could cause damage. Stability in the environment supports stability within the frog's body. As time passes, the frog remains in this condition without change. Its internal systems are paused and its energy use is minimal. This state can be maintained for extended periods as long as the surrounding environment remains cold. The frog does not need to move, feed, or breathe during this time. Its survival depends entirely on the controlled state it has entered and the protections built into its biology. In contrast, the bear, the ground squirrel, and the bat continue to maintain low levels of activity. Their hearts beat slowly, their breathing continues, and their bodies use stored energy at a controlled rate. These animals remain in a reduced state, but they do not pause their biological processes completely. This difference highlights the range of survival strategies used in cold environments. The moment freezing begins for the wood frog represents one of the most extreme transitions in the natural world. It is the point at which normal biological activity gives way to a controlled suspension. This process is not accidental. It is the result of precise preparation and adaptation, allowing the frog to survive conditions that would otherwise be fatal. Each step in the process is guided by internal systems that respond to the environment with accuracy. Through this transition, the wood frog demonstrates how life can persist even when conditions move beyond what is normally considered survivable. By allowing freezing to occur in a controlled way, it avoids the damage that would otherwise result. This ability reflects a deep connection between the body and the environment, where survival depends on alignment rather than resistance. As the cold continues and winter settles fully into place, the frog remains beneath the ice, unchanged and stable. Other animals remain within their own forms of reduced activity, each following a path shaped by their biology. Together, these examples show that survival in the cold is not defined by a single method, but by a range of adaptations that allow life to continue in different ways. This moment marks the completion of the transition from preparation to survival. The frog has entered its frozen state, the bear rests within its den, the ground squirrel remains deep within its burrow, and the bat hangs quietly in its cave. Each has reached a point where energy use is minimized and stability is maintained. From this point forward, survival depends on maintaining this balance until conditions begin to change. As winter continues, the wood frog stays in a frozen state beneath layers of snow and ice. Its body is still and unchanged, preserved in the condition it entered when freezing first began. Ice remains within its tissues, and the internal processes that once supported movement and activity are now paused. There is no breathing, no active circulation, and no visible sign of life. Yet within this stillness, the structure of the frog's body remains intact, held together by the protective changes that took place before and during freezing. Inside the frog, the distribution of water and protective compounds holds steady. Much of the water that once filled its cells has shifted into spaces where freezing causes less harm. Within the cells themselves, concentrated compounds continue to protect delicate structures. These substances help prevent the formation of damaging ice crystals and maintain the integrity of the cell walls. This balance allows the frog's tissues to remain preserved, even as the surrounding environment stays far below freezing. Over time, the frozen state does not require active adjustment. The frog does not respond to daily changes in temperature in the way an active animal would. Instead, it relies on the stability of its internal condition and the consistency of the environment around it. As long as temperatures remain low, the frozen state is maintained without disruption. This absence of change is what allows the frog to survive for extended periods, even when conditions remain harsh. The environment plays a central role in supporting this stability. Snow acts as a layer of insulation, reducing sudden shifts in temperature. The ground beneath the frog provides a relatively stable surface, limiting exposure to extreme fluctuations. Together, these conditions create a consistent environment where the frozen state can be maintained safely. The frog's survival depends not only on its internal adaptations, but also on the steadiness of its surroundings. While the wood frog remains completely frozen, other animals maintain different forms of reduced activity. A bear, resting within its den, continues to breathe slowly and relies on stored fat to sustain its body. A ground squirrel, deep within its burrow, stays in a state of deep hibernation, with its body temperature low but not frozen. A bat, suspended in a cave, continues to breathe at a slow rate, maintaining essential functions. These animals remain alive through controlled reduction, while the frog remains preserved in a state of suspended activity. The difference between these states highlights the unique nature of the frog's survival strategy. A bear must maintain a steady internal temperature to prevent damage, and its body keeps function at a reduced level. A ground squirrel lowers its temperature significantly, but avoids freezing by staying within a controlled range. The wood frog allows its body to freeze, relying on chemical protection rather than continuous function. This distinction shows how different species solve the same challenge in very different ways. During this period, energy use within the frog is extremely limited. The processes that normally require energy have slowed to a near-complete stop. Unlike a bear or a bat, which must continue to use energy to support breathing and circulation, the frog's needs are minimal. This allows it to remain in this state without relying on stored energy in the same way as other animals. Its survival depends on preservation rather than ongoing function. The length of time the frog can remain frozen depends on environmental conditions. In regions where winter lasts for extended periods, the frog may remain in this state for weeks or even months. Throughout this time, its body stays steady, protected from damage by the balance of internal chemistry and external stability. This extended stillness is not a sign of inactivity, but a carefully maintained condition that supports survival. Despite the lack of visible activity, the frog's body is not unstructured. Cells remain organized, and tissues retain their form. The protective compounds within its body continue to stabilize these structures, ensuring that they can function again when conditions change. This preservation is essential, as any damage during the frozen state would affect the frog's ability to recover later. Other animals rely on ongoing regulation during this time. A ground squirrel may occasionally adjust its body temperature, briefly increasing it before returning to a deeper state. A bat may shift slightly within its cave, maintaining balance and stability. A bear may change position within its den, though its overall activity remains low. These small adjustments allow these animals to maintain their reduced states over time. The frog, however, stays steady, relying entirely on its preserved condition. As winter progresses, the frozen state continues without interruption. The surrounding snow and ice remain in place, and temperatures stay low enough to prevent thawing. This consistency is important, as repeated freezing and thawing could cause damage. The stable environment allows the frog to remain in a single, continuous state until the season begins to shift. The simplicity of this state is one of its strengths. By reducing activity to a minimum and relying on preservation, the frog avoids the need for constant adjustment. There is no need to search for food, regulate temperature actively, or maintain circulation. The body exists in a state where change is minimized and stability is maintained over time. This approach allows survival under conditions that would otherwise require constant effort. In contrast, animals such as bears, ground squirrels, and bats must continue to regulate their internal systems. Their survival depends on balancing reduced activity with ongoing function. They must manage energy use carefully, ensuring that their reserves last through the winter. The frog avoids this challenge by entering a state where energy use is nearly eliminated, relying instead on the integrity of its preserved tissues. The frozen state represents one of the most extreme forms of adaptation to cold environments. It shows how life can persist even when conditions move beyond what is normally considered survivable. By allowing its body to freeze in a controlled way, the wood frog avoids the damage that would otherwise occur. This ability reflects a precise alignment between the body's internal systems and the external environment. As the cold season continues, the frog remains beneath the surface, unchanged and stable. Other animals remain within their own forms of reduced activity, each following a strategy suited to their biology. Together, these examples show that survival in the cold is not defined by a single approach, but by a range of adaptations that allow life to continue in different ways. This period of stillness is not the end of the process, but a stage within it. The frog's body remains prepared for the moment when conditions begin to change. When temperatures eventually rise, the frozen state will begin to reverse, and the systems that have been paused will gradually return to activity. Until that moment arrives, the frog remains preserved, held in a stable condition that allows it to endure the deepest cold of winter. As winter begins to release its hold and temperatures slowly rise, the conditions surrounding the wood frog begin to change. The ice that has held its body in place for so long starts to soften, and the frozen ground beneath it begins to warm. This shift does not happen suddenly. It develops gradually, allowing the frog's body to respond in a controlled way. The same steady process that led into freezing now begins to reverse, guided by the environment. As the ice around the frog begins to melt, the first internal changes take place. Water that had formed into ice within its tissues starts to return to a liquid state. This transition is slow and even, preventing sudden shifts that could damage delicate structures. The protective compounds that were concentrated within the frog's cells continue to play a role, helping maintain stability as the ice melts. This controlled thawing ensures that the body can begin to function again without disruption. As more ice melts, water gradually returns to the cells from the spaces where it had been drawn during freezing. This movement restores the balance within the frog's tissues. Cells begin to regain their shape, and internal structures return to their original positions. This process must remain steady, as rapid changes could affect the integrity of the cells. The frog's body manages this transition with precision, reversing the earlier process step by step. The return of liquid water allows biological activity to begin again. The frog's internal systems, which have been paused, start to resume their functions. At first, these changes are subtle and not immediately visible. The body remains still as its internal processes slowly re-establish themselves. This quiet reactivation is essential, allowing the frog to move from a frozen state back into active life without instability. One of the most significant moments in this process is the return of circulation. As internal conditions stabilize, the heart begins to beat again. This does not occur instantly or at full strength. The heartbeat starts slowly, gradually increasing as the body continues to warm. With each beat, circulation begins to move fluid through the body once more, delivering oxygen and nutrients to cells that have remained preserved throughout the winter. Breathing also returns during this stage. As circulation resumes, the need for oxygen increases, and the frog begins to take its first breaths since entering the frozen state. These breaths are slow and steady, matching the gradual pace of reactivation. The coordination between breathing and circulation ensures that the body can support its returning functions without sudden strain. As these systems come back online, the frog's body temperature keeps rise, following the warming environment. This increase supports the reactivation of chemical processes within the body. Enzymes that had been inactive begin to function again, allowing cells to carry out the tasks required for normal activity. This restoration of function happens in stages, ensuring that each system returns in balance with the others. While the wood frog undergoes this process of thawing and revival, other animals experience a different kind of transition. A bear within its den begins to increase its activity, its body slowly returning to a higher metabolic rate. A ground squirrel emerges from deep hibernation, raising its body temperature and resuming movement. A bat within a cave begins to adjust to changing conditions, increasing its activity as temperatures rise. These animals restart their systems, but they do so from a state that remained active at a reduced level. The frog's transition is more dramatic because it begins from a state where activity had nearly stopped. Its return to function requires the reactivation of systems that had been completely paused. This difference highlights the unique nature of its adaptation. While other animals resume reduced activity, the frog effectively restarts its biological processes. As thawing continues, movement gradually returns. The frog's muscles, which have remained still for an extended period, begin to regain function. This process is not immediate. The body must restore coordination and strength before movement becomes possible. The frog remains still during this stage, allowing its systems to stabilize before attempting to move. Once internal balance is restored, the frog begins to show signs of activity. Its body shifts slightly, and movement becomes possible again. This marks the final stage of the transition from frozen preservation to active life. The frog is no longer in a state of suspension. It has returned to a condition where it can respond to its environment. The success of this process depends on the precision of each step. The thawing must occur gradually, allowing water to return to cells without causing damage. Circulation and breathing must resume in coordination, ensuring that the body can support its functions. Each system must return at the right pace, maintaining balance throughout the transition. This careful regulation allows the frog to move from one extreme state to another without disruption. As the environment continues to warm, the frog fully resumes its activity. It moves from its position beneath the melting ice and returns to its surroundings. The conditions that once required it to freeze have passed, and the body has adapted once again to match the environment. This shift completes the cycle that began with preparation and freezing. The ability to thaw and return to life after freezing represents one of the most remarkable processes in the natural world. It shows how life can pause under extreme conditions and then resume when those conditions change. The wood frog demonstrates that survival is not always about continuous activity. It can also depend on the ability to stop and begin again in a controlled and stable way. Through this process, the frog reveals the full extent of its adaptation. From preparation to freezing, and from freezing to thawing, each stage is guided by precise biological control. The environment triggers these changes, and the body responds with accuracy. This connection between external conditions and internal function allows the frog to survive in a way that is both simple and highly effective. As spring continues and the environment stabilizes, the frog returns to its normal patterns of activity. The frozen state is left behind, and the systems that supported survival during winter now support active life once again. This transition completes the cycle, showing how the body can move between extremes while maintaining the ability to function. The wood frog's journey through freezing and revival provides a clear example of how life adapts to changing conditions. It demonstrates that survival is not limited to avoiding extreme environments. It can also involve meeting those conditions directly, adjusting internal systems to match what the environment demands. Through this process, the frog continues its life, having endured the deepest cold through precise and controlled adaptation. As the wood frog fully returns to activity, its recovery is not simply the result of warming temperatures. It is guided by internal systems that control how and when its body resumes function. The same biological processes that allowed the frog to enter a frozen state now regulate its return. This transition is carefully controlled, ensuring that each system resumes activity in a stable and coordinated way. The frog's body responds to environmental cues that signal the end of winter. Rising temperatures provide one of the most direct signals, indicating that freezing conditions are no longer present. At the same time, increasing daylight plays an important role in guiding internal rhythms. These changes are detected by the frog's body, triggering adjustments that support recovery. The transition is not based on a single signal, but on a combination of environmental factors that together indicate a change in season. Hormones play a central role in this process. As conditions shift, the frog's internal chemistry begins to change, regulating how its body moves from a state of suspended activity back to normal function. These hormonal signals influence metabolism, circulation, and overall activity levels. They ensure that the return to activity happens gradually, preventing sudden changes that could disrupt the body's balance. As recovery continues, the coordination between systems becomes clear. The return of circulation supports the delivery of oxygen and nutrients, while breathing adjusts to meet the body's increasing demand. At the same time, metabolic processes begin to rise, allowing energy to be used more actively. Each of these systems works together, creating a controlled and steady return to function. This coordination reflects the body's ability to manage complex transitions with precision. The timing of these changes is essential for survival. If the frog were to resume full activity too quickly, its systems might not be prepared to support it. If recovery were delayed, it could miss the opportunity to take advantage of improved conditions. The body balances these factors through internal regulation, ensuring that recovery happens at the right pace. This timing is guided by both environmental signals and internal biological rhythms. Other animals also rely on similar forms of regulation as they emerge from their reduced states. A bear, waking from its den, begins to increase its activity as its metabolism rises. A ground squirrel gradually raises its body temperature and resumes movement. A bat responds to changing conditions within its cave, adjusting its activity as temperatures increase. Each of these animals depends on internal systems that coordinate their return to activity. The wood frog's recovery remains distinct due to the extent of its earlier state. Its systems had paused almost completely, requiring a more complete reactivation. Despite this, the underlying principle remains the same. Internal signals guide the process, ensuring that each system returns in coordination with the others. This allows the frog to move from a frozen state to active life without instability. Environmental conditions continue to influence this process as recovery progresses. Stable temperatures support a steady increase in activity, while fluctuations may slow the transition. Light cycles reinforce internal rhythms, helping align the frog's behavior with the changing season. These external factors work alongside internal systems, shaping how recovery unfolds over time. As the frog becomes fully active, its body reaches a new balance. Metabolism returns to a level that supports movement and feeding. Circulation and breathing operate normally, and energy is used to support daily activity. This state reflects the completion of the recovery process, where the body has moved from suspension back to function in a controlled way. The coordination seen in this transition highlights the importance of regulation in survival. From preparation to freezing, and from freezing to recovery, each stage depends on internal systems that respond to environmental change. These systems ensure that the body holds steady, even as it moves between very different states. This ability to regulate function over time is central to survival in changing conditions. Through this process, the wood frog demonstrates how life can adapt not only to extreme cold, but also to the transition out of it. The same precision that allowed it to survive freezing now supports its return to activity. Each step is guided by internal signals, ensuring that the body remains balanced as conditions improve. This connection between the body and the environment allows the frog to continue its life cycle. Other animals follow similar patterns of regulation, though their transitions may be less extreme. A bear gradually increases its activity as its body adjusts to warmer conditions. A ground squirrel emerges from its burrow and resumes movement. A bat begins to leave its resting place as its environment changes. In each case, internal systems coordinate the return to activity, guided by environmental cues. The process of recovery is not a single event, but a continuation of the same cycle that began with preparation. Environmental signals trigger internal responses, and the body adjusts accordingly. This cycle allows animals to move between states of activity and inactivity in a controlled way, maintaining stability throughout. As spring fully arrives, the wood frog continues its activity within an environment that now supports growth and movement. The frozen state has passed, and the systems that once slowed to a near stop are now fully active. This transition reflects the ability of the body to respond to change with precision, ensuring survival through both extreme cold and the return to warmer conditions. Not all animals survive the cold in the same way, even when they share the same environment. The wood frog remains one of the most extreme examples, allowing its body to freeze and later return to activity. However, many other species follow different patterns that reflect their size, biology, and surroundings. These variations show that there is no single method for surviving winter, but rather a range of strategies shaped by each animal's needs. Some animals enter long periods of inactivity that last for much of the winter. A bear, resting within its den, may remain in a low activity state for an extended period, relying on stored fat to maintain its body. Its heart rate slows and its movement is minimal, but it does not reach the same level of suspension seen in the wood frog. This form of hibernation allows the bear to conserve energy while still maintaining a stable internal state. Other animals follow shorter cycles of inactivity. A ground squirrel, for example, may enter deep hibernation for a period of time, then briefly return to a more active state before lowering its body temperature again. These cycles allow it to maintain internal balance while still conserving energy. A bat may also shift between deeper and lighter states of inactivity, depending on conditions within its cave. These patterns show that hibernation does not always occur as a single continuous phase. In contrast, the wood frog does not follow cycles of reduced activity. Instead, it enters a frozen state and remains in that condition until environmental changes allow it to thaw. Its survival depends on maintaining this state without interruption. This approach differs from animals that adjust their activity repeatedly, highlighting the range of strategies used to endure the same conditions. The length of inactivity also varies widely between species. Some animals remain inactive for only short periods, responding quickly to changes in temperature, Others remain in reduced states for weeks or months, depending on the severity of winter. A bear may remain within its den for an extended time, while a ground squirrel alternates between deeper and lighter states. These differences reflect the relationship between each species and its environment. Environmental conditions play a major role in shaping these patterns. In regions where temperatures fluctuate, animals may need to adjust their activity more frequently. A bat in a cave may respond to small changes in temperature, shifting its state to maintain balance. In more stable environments, animals can remain in a consistent state for longer periods. The wood frog depends on stable freezing conditions to maintain its suspended state, while other animals rely on consistent temperatures to support hibernation. Biology also determines how each species responds to the cold. Larger animals tend to maintain higher body temperatures and rely on stored energy over time. Smaller animals often allow their body temperature to drop more significantly, reducing energy use to a greater extent. A ground squirrel can lower its temperature far more than a bear, while a bat can match the conditions of its cave. These differences show how size and physiology influence survival strategies. Flexibility is another important factor in how animals respond to winter. Some species can adjust their behavior based on changing conditions, shifting between activity and inactivity as needed. A bat may leave its resting place if temperatures rise, then return to a reduced state when conditions cool again. A ground squirrel may briefly increase its body temperature before returning to deeper hibernation. These adjustments allow animals to respond to variability in their environment. The wood frog represents a more fixed strategy, where survival depends on maintaining a specific state rather than adjusting frequently. Once frozen, it remains in that condition until the environment changes. This lack of flexibility is balanced by the precision of its adaptation, which allows it to tolerate conditions that other animals avoid. It shows that both flexible and fixed strategies can support survival, depending on the species. Across all of these variations, a common pattern remains. Animals reduce activity, conserve energy, and respond to environmental conditions in ways that support survival. The exact method differs, but the goal is the same. A bear resting in its den, a ground squirrel cycling through hibernation, a bat adjusting within its cave, and a wood frog frozen beneath the ice all reflect different versions of this principle. These differences highlight the diversity of life and the many ways it adapts to challenging conditions. Each species has developed a strategy that aligns with its environment, allowing it to survive periods of cold and limited resources. This diversity ensures that life continues across a wide range of conditions, even when those conditions become severe. Through these variations, it becomes clear that survival in the cold is not defined by a single approach. It is shaped by a combination of environmental factors, biological traits, and internal regulation. Each animal follows a path that supports its survival, whether through continuous hibernation, cycles of inactivity, or tolerance of freezing itself. The wood frog remains a central example of how extreme adaptation can support survival, while other animals demonstrate different methods that achieve the same result. Together, they show that life can persist in many forms, each carefully aligned with the conditions it must endure. As the wood frog remains beneath the frozen surface, Its survival depends on the precise way freezing has taken place within its body. This process is not simply a result of cold temperatures. It is shaped by how water moves, how cells respond, and how internal compounds maintain stability. Each part of this process works together, allowing the frog to endure conditions that would otherwise damage living tissue. When freezing first began, water did not freeze evenly throughout the frog's body. Instead, ice formed in specific areas where it would cause the least harm. Much of the freezing occurred outside the cells, in spaces between tissues. This controlled placement is important, as ice forming directly inside cells could disrupt their structure. By allowing freezing to occur in these external areas, the frog reduces the risk of internal damage. At the same time, water inside the cells was drawn outward. This movement helps prevent the formation of ice within the cells themselves. As water leaves the cells, their internal environment becomes more concentrated. This concentration is supported by protective compounds that were produced earlier. These compounds stabilize the cells, helping them maintain their structure even as conditions change. One of the most important of these compounds is glucose. As freezing begins, glucose levels within the frog's body increase significantly. This increase is not related to energy use, but to protection. Glucose acts as a stabilizing substance, helping to preserve the integrity of cells and tissues. It reduces the impact of freezing and helps prevent damage that would otherwise occur when ice forms. This combination of water movement and chemical protection creates a stable frozen state. The frog's tissues remain intact, even though a large portion of its body contains ice. The cells are not active, but they are preserved. Their structure remains organized, allowing them to function again when conditions improve. This preservation is what allows the frog to survive the freezing process. As time passes, the frozen state stays steady. The frog does not adjust or respond to daily shifts in temperature in the way an active animal would. Instead, it stays in a stable condition, supported by the balance of ice, water, and protective compounds within its body. This lack of change is essential, as repeated freezing and thawing could disrupt the structure of its tissues. The environment around the frog supports this stability. Snow and ice create a layer that reduces sudden changes in temperature. The ground beneath provides a steady surface, limiting exposure to rapid fluctuations. These conditions allow the frog to remain in a consistent state, where its internal balance is maintained over time. Without this stability, the freezing process would be more difficult to sustain safely. Other animals rely on different methods to avoid these conditions entirely. A ground squirrel, for example, lowers its body temperature but does not allow itself to freeze. Instead, it remains just above freezing, maintaining a controlled internal state. A bat relies on the stable temperature of its cave to avoid extreme fluctuations. A bear maintains a higher body temperature within its den, using stored energy to remain stable. Each of these animals avoids the need to tolerate ice within its tissues. The wood frog's approach is different because it allows freezing to occur, but only in a controlled way. This requires a level of precision that depends on both internal preparation and environmental stability. The body must ensure that ice forms in the correct places, that cells remain protected, and that the overall structure is preserved. Each part of this process contributes to the frog's survival. Within the frozen tissues, biological activity is almost completely paused. Chemical reactions occur at an extremely slow rate, and energy use is minimal. This state allows the frog to remain in this condition for extended periods without relying on stored energy in the same way as other animals. Its survival depends on preservation rather than ongoing function. The longer the frozen state continues, the more important stability becomes. Any disruption to the balance between ice and protective compounds could affect the frog's ability to recover later. This is why consistent environmental conditions are essential. The frog's body is prepared for freezing, but it depends on the environment to maintain that state safely over time. Even in this state, the organization of the frog's body remains intact. Cells, tissues, and internal structures retain their arrangement, supported by the protective compounds within them. This organization is critical, as it allows the body to return to function once thawing begins. Without this preservation, the transition back to activity would not be possible. The wood frog's ability to manage freezing in this way shows how precisely biological systems can adapt to extreme conditions. By controlling where ice forms, how water moves, and how cells are protected, the frog maintains a stable state that supports survival. This process is not visible from the outside, but it defines how the frog endures the cold. As winter continues, the frog remains in this preserved condition, unchanged and stable beneath the ice. Other animals continue their own forms of reduced activity, each relying on a different method to survive. The frog, however, stays in a state where freezing itself is part of the solution. This approach allows it to exist in an environment where other strategies would not be possible. Through this deeper view of freezing, it becomes clear that survival depends on more than simply enduring cold temperatures. It requires precise control over internal systems and a strong connection to the environment. The wood frog demonstrates how this control allows life to persist, even when conditions move beyond what is normally considered survivable. As winter settles fully into place, time passes slowly around the wood frog, yet within its frozen body, there is no sense of movement or change. Beneath layers of snow and ice, it remains exactly as it was when freezing first completed. The surface above may shift slightly with wind or falling snow, but the space surrounding the frog remains steady and quiet. The cold holds everything in place, creating an environment where change is minimal and stability is constant. Days and nights continue to pass, marked only by subtle changes in light above the frozen ground. Sunlight may reach the surface during the day, warming the outer layer slightly before fading again as night returns. Beneath this surface, the frog stays steady. Its body does not respond to these daily cycles in the way it would during active life. Instead, it exists in a state where time moves forward without requiring internal adjustment. Within its tissues, the balance established during freezing remains intact. Ice keeps occupy the spaces between cells, while the cells themselves remain protected by the compounds that surround them. There is no movement of fluid, no shifting of structures, and no visible sign of activity. This stillness allows the frog to remain preserved, maintaining the organization needed for future recovery. The quiet of this state extends across the surrounding environment. Beneath the snow, the ground holds a consistent temperature that prevents sudden changes. This stability supports the frog's condition, allowing it to remain frozen without disruption. The absence of rapid temperature shifts is essential, as repeated freezing and thawing could disturb the balance within its body. Other animals experience time differently during this period. A ground squirrel, deep within its burrow, may shift slightly as its body cycles through periods of deeper and lighter hibernation. A bat, hanging within a cave, may adjust its position or breathing over time. A bear, resting in its den, keeps use energy slowly, maintaining its body throughout the winter. Each of these animals remains connected to the passage of time through subtle activity. The wood frog, however, remains separate from these changes. Its body does not cycle through different states. It does not adjust its position or regulate its temperature actively. Instead, it stays in a single, continuous condition, preserved by the balance established during freezing. This difference highlights the unique nature of its adaptation, where survival depends on maintaining stillness rather than responding to change. As the season progresses, the environment keeps reinforcing this stability. Snow accumulates and settles, creating a thicker layer that insulates the ground. This insulation reduces the impact of external temperature changes, helping maintain a consistent condition beneath the surface. The frog remains within this protected space, unaffected by fluctuations that occur above. Time continues to move forward in a steady and predictable way. Weeks pass, and the frozen state stays steady. The frog does not require energy in the way other animals do during this time. Its processes remain paused, allowing it to exist without the need for continuous function. This absence of activity allows it to endure long periods of cold without the demands placed on other forms of life. The simplicity of this state is one of its most effective features. By remaining unchanged, the frog avoids the need to adjust or respond to its environment. It does not need to search for food, regulate its body actively, or maintain ongoing biological processes. Its survival depends on preservation rather than action, allowing it to remain stable over time. In contrast, animals such as bears and ground squirrels must manage their energy carefully throughout the winter. A bear keeps rely on stored fat, using energy slowly to maintain essential functions. A ground squirrel cycles through states of reduced activity, balancing conservation with internal regulation. A bat stays in a low energy state, adjusting as needed to maintain stability. Each of these animals depends on ongoing processes to survive. The wood frog's strategy removes the need for this continuous regulation. Its body remains fixed in a condition where change is minimized. This allows it to exist without the demands of active survival, relying instead on the preservation of its structure. The environment supports this condition by maintaining consistent cold temperatures. As winter continues, the frozen state becomes a steady background to the passing season. The frog remains beneath the surface, unchanged, while the world above continues its cycle. Snow may fall, wind may move across the surface, and temperatures may shift slightly, but the frog remains in the same preserved condition. This separation from the environment's activity is what allows it to endure. Eventually, subtle changes begin to appear in the environment. Temperatures rise slightly during the day, and the strength of sunlight increases as the season begins to shift. These changes are gradual and do not immediately affect the frog's condition. The frozen state remains intact, supported by the stability that has been maintained throughout the winter. This long period of stillness represents one of the most controlled forms of survival in nature. By remaining unchanged, the wood frog avoids the risks associated with ongoing activity in a harsh environment. Its body is preserved in a way that allows it to endure extended cold without the need for energy or movement. Through this slow passage of time, the frog demonstrates how survival can depend on stillness as much as action. While other animals adjust and respond to the environment, the frog stays in a condition where change is unnecessary. This approach allows it to exist quietly beneath the surface, waiting for the moment when conditions will allow it to return to activity. As the season gradually moves toward warmer conditions, the stage is set for the next transition. The frozen state has been maintained with precision, and the frog remains intact and stable. When the environment changes enough to allow thawing, the process of returning to activity will begin once again, guided by the same balance that has supported it through the cold. As the wood frog remains preserved beneath the ice, its condition highlights a clear difference between its survival strategy and that of many other animals. While the frog allows its body to freeze and pause its internal activity, mammals such as bears, ground squirrels, and bats rely on maintaining a reduced but active state. This distinction defines two different approaches to surviving the same cold environment. One depends on preservation through freezing, while the other depends on controlled reduction of function. The wood frog enters a state where its internal systems are almost completely paused. Ice forms within its tissues, and processes such as circulation and breathing stop. Its survival depends on the stability of its cells and the protective compounds within them. In contrast, a bear resting within its den continues to breathe slowly and maintain circulation. Its heart rate decreases, but it does not stop. The bear's body remains active at a reduced level, using stored energy to sustain itself over time. A ground squirrel represents a deeper level of hibernation among mammals, yet it still differs from the frog. Its body temperature drops significantly, sometimes approaching the temperature of its surroundings. Its heart rate slows, and its breathing becomes minimal. However, it avoids freezing by remaining within a controlled range. Its cells continue to function, even at a reduced level, allowing it to maintain internal balance. This controlled reduction contrasts with the frog's complete suspension of activity. A bat, hanging within a cave, also relies on a reduced but active state. Its body temperature decreases, and its metabolism slows, but it continues to breathe and maintain circulation. The stable environment of the cave supports this condition, allowing the bat to conserve energy without entering a frozen state. This approach requires ongoing regulation, as the bat must adjust to small changes in temperature over time. The difference between these strategies is most visible in how energy is used. The wood frog, once frozen, uses almost no energy to maintain its condition. Its processes are paused, allowing it to exist without the need for continuous energy input. Mammals, however, must rely on stored energy throughout their period of inactivity. A bear depends on fat reserves to maintain its body, while a ground squirrel and a bat use energy slowly to support reduced function. This ongoing energy use requires careful balance to ensure survival. The role of temperature also differs between these approaches. The wood frog allows its body temperature to match the freezing environment, relying on internal protection to survive. Mammals regulate their temperature more carefully, avoiding conditions that would lead to freezing. A bear maintains a relatively stable internal temperature, while a ground squirrel lowers its temperature significantly but remains above freezing. These differences reflect how each species balances conservation with the need to maintain function. The level of internal control required also varies. For the wood frog, the critical moment occurs during the transition into freezing, where its body must prepare and protect its cells. Once frozen, the need for active regulation decreases. Mammals, on the other hand, must continuously regulate their internal systems throughout hibernation. Their bodies adjust heart rate, breathing, and metabolism over time, maintaining stability through ongoing control. Flexibility is another point of contrast. Mammals can adjust their state in response to environmental changes. A ground squirrel may briefly raise its body temperature before returning to a deeper state. A bat may become more active if conditions within its cave change. A bear may respond to disturbances within its den. These adjustments allow mammals to remain responsive to their environment. The wood frog, once frozen, does not have this flexibility. Its survival depends on remaining in a stable, unchanged condition until thawing begins. The risks associated with each strategy also differ. The wood frog must rely on the precise control of ice formation and cellular protection. Any disruption to this balance could affect its ability to recover. Mammals face the challenge of maintaining their energy reserves over time. If their stored energy is insufficient, they may not survive the winter. Each strategy carries its own risks, shaped by the requirements of the process. Despite these differences, both approaches share a common goal. Each animal must reduce energy use, maintain stability, and respond to environmental conditions in a way that supports survival. The methods vary, but the outcome remains the same. A wood frog beneath the ice, a bear within its den, a ground squirrel in its burrow, and a bat in its cave all endure the cold through adaptations that align their bodies with the environment. These contrasting strategies highlight the diversity of life and its ability to adapt to extreme conditions. The wood frog demonstrates how survival can depend on allowing freezing to occur in a controlled way. Mammals show how reducing activity while maintaining function can achieve the same result. Together, these approaches reveal the range of solutions that exist for surviving the cold. Through this comparison, it becomes clear that survival is not defined by a single method. It depends on how each species balances energy use, temperature, and internal control. The wood frog represents one extreme, where activity is paused almost completely. Mammals represent another, where activity is reduced but maintained. Both approaches reflect a precise connection between the body and the environment. As winter continues, these different strategies remain in place, each supporting survival in its own way. The wood frog remains frozen and preserved, while mammals continue their reduced but active states. Each follows a path shaped by its biology, demonstrating how life can persist under the same conditions through different forms of adaptation. As the wood frog moves through each stage of preparation, freezing, and recovery, its survival depends on more than environmental conditions alone. Beneath these visible changes, internal control systems guide every transition. These systems determine when the frog prepares for freezing, when it allows its body to enter a suspended state, and when it begins to return to activity. This coordination ensures that each stage happens at the correct time and in the correct sequence. The process begins with the detection of environmental signals. As daylight becomes shorter and temperatures begin to fall, the frog's body recognizes these changes through sensory pathways that respond to light and temperature. These signals do not act independently. Instead, they combine to form a pattern that indicates the approach of winter. The frog's body responds to this pattern gradually, adjusting its internal state in preparation for the conditions ahead. Hormones play a central role in translating these signals into physical changes. As environmental cues shift, hormone levels begin to adjust, influencing how the body uses energy, how it prepares its tissues, and how it regulates activity. These chemical signals move through the body, coordinating changes across multiple systems at the same time. This ensures that preparation is not limited to a single function, but occurs throughout the entire organism. As freezing approaches, these internal signals guide the production of protective compounds. The increase in glucose and other stabilizing substances does not happen randomly. It is triggered by hormonal changes that direct the body to begin this process at the appropriate time. This coordination ensures that the frog is prepared before freezing conditions fully develop, reducing the risk of damage when ice begins to form. During the transition into freezing, internal control remains essential. The movement of water out of cells, the formation of ice in specific areas, and the stabilization of tissues all occur in a controlled manner. These processes are guided by the same regulatory systems that began preparing the body earlier. This continuity allows the frog to move from one stage to the next without disruption, maintaining stability throughout the transition. Once the frog is fully frozen, the role of active regulation decreases, but the results of earlier control remain in place. The protective compounds continue to stabilize cells, and the distribution of water and ice remains balanced. The frog does not actively adjust its condition during this time, but the structure established during earlier stages ensures that it remains preserved. This shows how preparation and regulation before freezing support stability during the frozen state. As environmental conditions begin to change, internal control systems become active once again. Rising temperatures and increasing daylight provide signals that the frozen state can begin to reverse. The frog's body responds to these cues by gradually reactivating its internal processes. This response is not immediate. It develops in stages, allowing each system to return to function in a controlled way. Hormonal signals guide the process of thawing and recovery. As conditions improve, these signals influence the return of circulation, breathing, and metabolic activity. The heart begins to beat again, and oxygen begins to move through the body. These changes are coordinated so that no single system becomes active too quickly. This balance is essential for maintaining stability during the transition. The timing of these changes is critical. If the frog were to begin thawing too early, it could be exposed to conditions that would lead to refreezing. If recovery were delayed too long, it could miss the opportunity to return to an environment that supports activity. Internal control systems balance these risks by responding to multiple environmental signals, ensuring that recovery begins at the appropriate time. Other animals rely on similar forms of internal control, though their processes differ in detail. A bear adjusts its metabolism and activity levels in response to seasonal changes, guided by hormonal signals. A ground squirrel cycles between deeper and lighter states of hibernation, with internal systems regulating these shifts. A bat responds to changes within its environment, adjusting its activity based on temperature and conditions within its cave. In each case, internal regulation ensures that the body responds appropriately to external changes. The wood frog's system of control is distinct because it must manage more extreme transitions. It must guide the body into a frozen state where activity nearly stops, and later reverse that process without causing damage. This requires precise coordination across multiple systems, from the production of protective compounds to the timing of recovery. Each step depends on internal signals that align the body with the environment. The coordination of these systems reflects the complexity of biological regulation. Environmental cues provide information, but it is the body's internal systems that interpret this information and respond to it. Hormones act as messengers, carrying signals that guide changes throughout the body. These signals ensure that each part of the organism responds in a way that supports overall stability. As the frog completes its recovery and returns to activity, these internal control systems continue to operate. They regulate metabolism, movement, and energy use, maintaining balance as conditions change. The same systems that guided preparation and freezing now support active life, ensuring that the frog remains aligned with its environment. Through this process, the wood frog demonstrates how survival depends not only on physical adaptation, but also on precise internal control. Each stage of its cycle is guided by signals that coordinate changes across the body. This coordination allows it to move between states of activity and suspension without losing stability. The connection between environmental signals and internal regulation forms the foundation of this adaptation. By responding to changes in light and temperature with controlled biological adjustments, the frog can survive conditions that would otherwise prevent life from continuing. This balance between external conditions and internal control defines how the wood frog endures the changing seasons. As the wood frog moves through its cycle of freezing and recovery, the environment does not simply surround it. The environment actively shapes each stage of its survival. Temperature, light, moisture, and seasonal timing all influence how the frog's body responds. These external conditions do not act in isolation. They work together to create a pattern that the frog's internal systems interpret and respond to with precision. Temperature remains the most direct influence on the frog's condition. As the air cools and the ground begins to freeze, the frog's body responds by slowing its activity and preparing for the transition into a frozen state. The rate at which temperatures fall can affect how quickly these changes occur. A gradual drop allows the frog to prepare steadily, while a rapid drop requires its body to respond more quickly. In both cases, the frog's survival depends on how well its internal systems align with the changing temperature. Light also plays an important role, even though it does not directly cause freezing. As days become shorter, the amount of daylight decreases, providing a reliable signal that winter is approaching. The frog's body responds to this change by adjusting internal rhythms that guide preparation. These adjustments influence hormone levels, which in turn regulate how the body stores energy and produces protective compounds. Light acts as an early signal, allowing the frog to begin preparing before temperatures become extreme. Moisture within the environment adds another layer to this interaction. The presence of water in the soil and surrounding leaf litter affects how freezing occurs around the frog. As moisture freezes, it contributes to the formation of ice that surrounds the frog's body. This external ice interacts with the frog's internal processes, influencing how freezing spreads through its tissues. The balance between moisture and temperature helps determine how stable the frozen state will be. The ground itself provides a form of stability that supports the frog's survival. Beneath the surface, temperatures tend to change more slowly than in the open air. This creates a more consistent environment where the frog can remain without experiencing sudden fluctuations. The layer of soil and leaf litter acts as a buffer, reducing the impact of rapid environmental changes. This stability allows the frog's internal systems to maintain balance during freezing. Snow further enhances this stability once it accumulates. Acting as an insulating layer, snow reduces the loss of heat from the ground and limits the effect of sudden temperature shifts. For the wood frog, this means that once it is frozen, it is less likely to experience repeated cycles of freezing and thawing. These cycles could disrupt the balance within its body. The presence of snow helps maintain a steady condition that supports long-term survival. While the wood frog depends on this stable interaction with its environment, other animals respond in different ways. A ground squirrel relies on the consistent temperature within its burrow, which protects it from extreme changes. A bat depends on the stable conditions within its cave, where temperature and humidity remain relatively constant. A bear selects a den that shields it from wind and cold, allowing it to maintain a reduced but stable state. Each animal interacts with the environment in a way that supports its particular strategy. The wood frog's interaction with its environment is unique because it does not avoid freezing conditions. Instead, it relies on the environment to provide the exact conditions needed for controlled freezing. The balance between temperature, moisture, and insulation determines whether the frog can enter and remain in a stable frozen state. This reliance on environmental precision makes its survival closely tied to the consistency of its surroundings. As winter continues, the interaction between the frog and its environment remains steady. The frozen ground, the insulating snow, and the low temperatures work together to maintain the frog's condition. There is little variation, and this lack of change supports the preservation of its internal structures. The frog does not need to respond actively during this time, as the environment maintains the conditions required for its survival. When the season begins to shift, the environment once again plays a central role in guiding change. Rising temperatures begin to soften the frozen ground, and melting snow introduces moisture back into the environment. These changes signal the beginning of the thawing process. The frog's body responds to these signals, gradually reversing the conditions that allowed freezing to occur. The timing of this transition depends on the coordination between environmental factors. Temperature must rise steadily, rather than fluctuating sharply, to allow a controlled thaw. Increased daylight reinforces the shift, supporting the frog's internal rhythms. Moisture from melting ice helps restore the balance within the frog's tissues. Each of these factors contributes to a smooth transition back to activity. Other animals also respond to these environmental changes as they emerge from their reduced states. A ground squirrel begins to increase its body temperature as conditions within its burrow warm. A bat becomes more active as the temperature within its cave rises. A bear leaves its den as food becomes available and conditions support movement. These responses show how environmental changes guide the return to activity across different species. For the wood frog, the environment provides both the conditions for freezing and the signals for recovery. Its survival depends on the precise alignment between its internal systems and the external world. This relationship is not passive. The frog's body interprets environmental signals and responds with adjustments that maintain balance. The environment and the body work together, creating a system that supports survival through changing conditions. This interaction highlights the importance of consistency in the environment. Sudden or extreme changes could disrupt the balance required for freezing and thawing. Stable conditions allow the frog to move through each stage without damage. This reliance on environmental stability reflects how closely the frog's survival is tied to the world around it. Through this connection, the wood frog demonstrates how life can adapt by aligning internal processes with external conditions. Its body does not act independently of the environment. Instead, it responds to it in a way that maintains stability over time. This balance allows the frog to endure both the deepest cold and the transition back to warmer conditions. As the cycle continues, the relationship between the frog and its environment remains central to its survival. Each stage, from preparation to freezing to recovery, depends on this interaction. The environment provides the signals and conditions, and the body responds with precise adjustments. Together, they create a system that allows life to persist even in the most challenging seasons. As the wood frog remains frozen beneath the surface, its condition reveals one of the most important differences between its survival strategy and that of other animals. While many animals reduce their energy use during winter, the frog moves beyond reduction and enters a state where energy use is nearly absent. This distinction defines two separate approaches to survival. One depends on using energy slowly over time, while the other depends on preserving the body without requiring continuous energy at all. For the wood frog, once freezing is complete, the need for energy becomes minimal. The processes that normally require energy, such as circulation, breathing, and active metabolism, have been paused. The body is no longer using energy to maintain these functions in the usual way. Instead, it relies on the preservation of its structure, supported by the protective compounds that remain within its cells. This allows the frog to exist without drawing heavily on stored energy during this period. In contrast, animals such as bears depend entirely on stored energy throughout the winter. A bear, resting within its den, continues to breathe, circulate blood, and maintain a stable internal temperature. These processes require energy, even though activity is reduced. The bear relies on fat reserves built during earlier months, using them slowly to sustain its body. This continuous use of energy must be carefully balanced, as the bear must maintain its condition until food becomes available again. A ground squirrel follows a different pattern, but it also depends on ongoing energy use. During deep hibernation, its metabolic rate decreases significantly, reducing the amount of energy required to maintain its body. However, its systems continue to function at a low level. Its heart beats slowly, and its breathing remains minimal but present. Energy is still being used, though at a reduced rate, allowing the squirrel to maintain internal stability over time. A bat, suspended within a cave, also relies on controlled energy use. Its metabolism slows, and its body temperature decreases, reducing the need for energy. However, it continues to breathe and maintain circulation, requiring a steady supply of energy from stored fat. The stable environment of the cave supports this process, allowing the bat to conserve energy while maintaining essential functions. The wood frog's strategy removes the need for this continuous energy use. By entering a frozen state, it avoids the demands placed on animals that must maintain even reduced levels of activity. Its survival depends on preserving its internal structures rather than actively supporting them. This allows it to endure long periods without relying on energy reserves in the same way as other animals. The difference in energy use also affects how each animal responds to time. A bear must manage its energy reserves carefully throughout the winter, ensuring that they last until conditions improve. A ground squirrel must balance its reduced energy use with occasional adjustments to maintain stability. A bat must continue to regulate its body within the conditions of its environment. Each of these animals remains connected to the passage of time through the gradual use of energy. The wood frog exists outside of this pattern. Once frozen, it does not experience time through ongoing energy use. Its condition holds steady, and its processes are paused. This allows it to endure extended periods without the need for adjustment or regulation. The absence of energy demand is what allows the frog to maintain this state without relying on continuous biological activity. The preparation phase plays a role in this difference. Before freezing, the frog produces protective compounds that allow its cells to survive without ongoing energy use. These compounds stabilize its tissues, reducing the need for active maintenance during the frozen state. In contrast, animals such as bears and ground squirrels prepare by storing energy that will be used throughout winter. Their survival depends on how effectively they can manage these reserves. The transition out of these states also reflects this contrast. When a bear begins to wake, it increases its metabolic rate and resumes using energy at a higher level. A ground squirrel raises its body temperature and returns to active function, requiring energy to support these changes. A bat adjusts its activity as conditions improve, increasing its energy use as it becomes more active. The wood frog, however, transitions from a state where energy use was nearly absent. As it thaws, its systems begin to restart, and energy use gradually resumes. This shift from minimal energy demand to active function is controlled and precise, allowing the frog to return to life without disruption. The difference between these transitions highlights the unique nature of its strategy. Despite these differences, all of these animals share a common goal. They must survive periods where energy is difficult to obtain. The methods they use reflect their biology and the environments they inhabit. Some rely on conserving energy through reduced activity, while others rely on preserving their bodies in a state that requires little to no energy use. The wood frog represents one extreme of this range. By entering a state where energy use is nearly eliminated, it avoids the need to manage reserves over time. Mammals such as bears, ground squirrels, and bats represent another approach where energy is conserved but still used continuously. These contrasting strategies show how life can adapt in different ways to the same challenge. Through this comparison, it becomes clear that survival in the cold is not defined by how much energy is used, but by how effectively that energy is managed or avoided. The wood frog demonstrates that in some cases, survival can depend on stepping outside of the normal requirements of energy use. Other animals show that reducing and controlling energy use can achieve the same result. As winter continues, these strategies remain in place, each supporting survival in its own way. The wood frog remains frozen and preserved, while other animals continue their reduced but active states. Together, they illustrate the range of adaptations that allow life to persist in environments where energy is limited and conditions are severe. As the wood frog remains frozen beneath the surface, its survival depends on maintaining a precise balance between stability and potential risk. The frozen state appears still and unchanging, yet it is supported by conditions that must remain consistent. The arrangement of ice, water, and protective compounds within the frog's body has been carefully established. This balance allows its cells to remain intact, but it also depends on the environment continuing to support that condition. One of the most important factors in maintaining stability is temperature consistency. The frog relies on steady cold conditions to remain frozen in a controlled way. If temperatures remain low, the balance within its tissues is preserved. However, if temperatures begin to rise and fall repeatedly, the frog could be exposed to cycles of partial thawing and refreezing. These cycles could disrupt the arrangement of ice and fluid within its body, increasing the risk of damage to its cells. The presence of snow plays a role in reducing this risk. A layer of snow acts as insulation, limiting how quickly temperatures change beneath the surface. This helps protect the frog from sudden warming during the day, followed by freezing at night. The stability created by this insulation allows the frog's internal condition to remain unchanged for longer periods. Without this layer, the environment would be more variable, increasing the potential for disruption. Moisture within the environment also contributes to stability. The frozen ground and surrounding ice help maintain a consistent condition that supports the frog's preserved state. If the environment were too dry, or if moisture levels changed rapidly, the balance within the frog's tissues could be affected. The relationship between temperature and moisture helps maintain the conditions required for safe freezing. While the wood frog depends on this stable environment, other animals manage risk in different ways. A ground squirrel reduces risk by remaining within a burrow where temperature changes are less extreme. A bat relies on the stable conditions within a cave, avoiding exposure to external fluctuations. A bear selects a den that protects it from wind and cold, allowing it to maintain a controlled internal state. Each animal reduces risk by choosing an environment that supports its survival strategy. The frog's strategy involves a different type of risk. By allowing its body to freeze, it depends on the precise control of internal processes. The protective compounds within its cells must remain effective, and the distribution of ice must stay balanced. Any disruption to this balance could affect the frog's ability to recover later. This makes stability essential throughout the entire frozen period. Time also plays a role in managing risk. The longer the frog stays in a stable frozen state, the more it depends on the environment continuing to support that condition. Extended periods of cold are necessary for maintaining this balance, but they must remain consistent. Sudden changes, even if brief, could introduce instability that affects the frog's survival. In contrast, animals that rely on reduced activity rather than freezing face different risks. A bear must manage its energy reserves carefully, ensuring that its stored fat lasts throughout the winter. If its reserves are insufficient, it may not survive until food becomes available again. A ground squirrel must balance its cycles of hibernation, maintaining internal stability while conserving energy. A bat must remain within an environment that supports its reduced state, adjusting if conditions change. These differences highlight how each survival strategy involves its own form of balance. The wood frog depends on preserving its structure without ongoing activity, while mammals depend on maintaining reduced but continuous function. Each approach requires stability, but the nature of that stability differs depending on the strategy. The transition out of the frozen state also involves risk. As temperatures begin to rise, the frog must thaw gradually to avoid damage. If thawing occurs too quickly, the return of water to cells could disrupt their structure. If thawing is uneven, some parts of the body may recover before others, affecting overall balance. The environment must provide conditions that allow a steady and controlled thaw. Other animals also face challenges during their return to activity. A bear must restore its metabolism and movement without exhausting its remaining energy. A ground squirrel must raise its body temperature and resume function in a balanced way. A bat must adjust to changing conditions while maintaining stability. Each transition requires careful coordination between internal systems and the environment. The wood frog's survival depends on how well it maintains balance across all stages of this cycle. From preparation to freezing, from freezing to stability, and from stability to thawing, each phase must occur under the right conditions. The environment provides the framework, and the frog's internal systems respond with precision. Despite these risks, the frog's adaptation remains highly effective. By aligning its internal processes with environmental conditions, it reduces the likelihood of disruption. The combination of protective compounds, controlled freezing, and stable surroundings allows it to endure extended periods of cold. This balance between stability and risk defines how the frog survives. Through this interaction, the wood frog demonstrates that survival in extreme conditions depends on more than adaptation alone. It requires maintaining a steady state where internal and external factors remain aligned. This balance allows life to persist even when conditions approach the limits of what is normally possible. As winter continues, the frog remains beneath the surface, supported by this balance. The risks remain present, but they are managed through the stability of the environment and the precision of its internal systems. This quiet equilibrium allows the frog to endure the cold, waiting for the moment when conditions will once again allow change. As winter continues over long periods, the wood frog remains in its frozen state, unchanged and steady beneath the surface. Days pass into weeks, and weeks extend into months, yet the condition of the frog remains constant. The balance established during freezing does not require adjustment over time. Instead, it is maintained through the stability of the environment and the structure preserved within its body. This ability to endure without change defines one of the most remarkable aspects of its survival. Throughout this extended period, the frog does not experience time in the way active animals do. There is no ongoing movement, no shifting of position, and no gradual use of energy to support continuous function. Its internal systems remain paused, held in a state that does not depend on daily regulation. This absence of activity allows the frog to remain preserved for as long as the surrounding conditions remain stable. The environment plays a central role in supporting this endurance. The frozen ground beneath the frog provides a steady base, while the layer of snow above acts as insulation against sudden changes. This combination creates a consistent space where temperature remains low and predictable. The frog's survival depends on this consistency, as it allows the internal balance established during freezing to remain undisturbed over time. Within its tissues, the arrangement of ice and protective compounds remains intact. There is no gradual breakdown or movement within the cells. The compounds that protect its internal structures continue to hold them in place, preventing damage that could occur over long periods. This preservation allows the frog to maintain its condition without requiring ongoing maintenance or repair. Other animals experience this passage of time differently. A bear resting within its den keeps rely on stored energy, slowly using fat reserves to maintain its body. Over weeks and months, this energy use accumulates, requiring careful balance to ensure survival. A ground squirrel, deep within its burrow, cycles through periods of reduced activity, occasionally adjusting its internal state to maintain stability. A bat, hanging within a cave, continues to breathe and regulate its body at a low level. Each of these animals remains connected to time through the gradual use of energy. The wood frog exists outside of this pattern. Its survival does not depend on managing energy reserves over time. Instead, it depends on maintaining a preserved state where energy use is nearly absent. This allows it to endure extended periods without the need for adjustment. The passage of time does not create the same demands on its body as its processes remain paused. This endurance requires a stable environment throughout the entire period. If conditions remain consistent, the frog can remain frozen for as long as winter lasts. However, if the environment changes too quickly, the balance within its body could be affected. The duration of survival is therefore closely linked to the reliability of the surrounding conditions. The simplicity of this state supports its effectiveness. By removing the need for continuous activity, the frog avoids the challenges faced by animals that must regulate their bodies over time. There is no need to conserve energy actively, no need to adjust to small environmental changes, and no need to manage internal systems on a daily basis. This absence of demand allows the frog to endure conditions that would otherwise require constant effort. In contrast, animals that rely on reduced activity must maintain their systems throughout the winter. A bear keeps circulate blood and regulate its body, even at a lower level. A ground squirrel balances its cycles of activity and rest, ensuring that its internal systems remain stable. A bat responds to changes within its cave, adjusting its condition as needed. These animals must remain active at a minimal level, which creates ongoing demands over time. The wood frog's approach removes these ongoing demands, replacing them with a state of preservation. This allows it to endure long periods without the need for energy or adjustment. Its survival depends on the integrity of its tissues and the stability of its environment, rather than on continuous biological function. As winter continues, the frozen state becomes a constant condition rather than a temporary phase. The frog remains beneath the surface, unchanged as the season progresses. Snow may fall, wind may move across the ground, and temperatures may shift slightly, but the frog remains in the same preserved state. This consistency allows it to endure without disruption. Eventually, subtle changes begin to appear in the environment. Temperatures may rise slightly during the day, and the intensity of sunlight begins to increase. These changes do not immediately affect the frog, but they signal that the long period of cold is beginning to shift. The frozen state remains intact, supported by the stability that has been maintained throughout the winter. The endurance of the wood frog demonstrates how survival can depend on maintaining a condition over time, rather than responding continuously to change. By entering a state where processes are paused and structures are preserved, it avoids the challenges associated with long-term activity in a harsh environment. This allows it to persist through conditions that would otherwise be difficult to survive. Other animals rely on endurance in different ways. A bear must ensure that its stored energy lasts through the entire winter. A ground squirrel must balance its reduced activity with occasional adjustments to maintain stability. A bat must remain within an environment that supports its low energy state over time. Each of these forms of endurance reflects a different approach to surviving extended cold. Through this long duration, the wood frog remains a clear example of how preservation can support survival. Its ability to maintain a stable state over weeks and months allows it to endure without the need for continuous function. This approach highlights the role of time as a factor in survival, where endurance depends on maintaining balance rather than adapting constantly. As the season gradually shifts, the frozen state prepares to give way to the next stage. The frog stays steady, but the environment begins to move toward conditions that will allow recovery. This long period of endurance sets the foundation for the transition that will follow, completing another phase in the cycle of survival. As winter begins to ease, the first signs of change appear slowly within the environment surrounding the wood frog. These changes are not sudden or dramatic. Instead, they develop gradually, almost unnoticed at first. Beneath the surface, where the frog remains frozen, the conditions that have supported its long period of stillness begin to shift. The balance between cold and warmth starts to move in a new direction, setting the stage for what will follow. Temperature is the most direct of these changes. During the day, the air above the frozen ground begins to warm slightly, even if only for short periods. This warmth does not immediately reach the frog, but it begins to affect the outer layers of snow and ice. The surface softens briefly before cooling again as night returns. These small changes repeat over time, creating a gradual pattern that signals the transition away from the deepest cold. Light also begins to change in a steady and predictable way. The length of daylight increases as the season progresses, bringing longer periods of sunlight to the surface. This increase in light does not directly thaw the frozen ground, but it provides a consistent signal that conditions are shifting. The wood frog's internal systems, though still in a suspended state, are influenced by these changes as part of the larger seasonal cycle. Beneath the snow, the insulating layer keeps playing an important role. It slows the movement of heat into the ground, preventing sudden changes that could disrupt the frozen state. This allows the transition to occur gradually rather than all at once. The frog holds steady within this environment, protected from rapid fluctuations while the overall conditions begin to adjust. Moisture within the environment also begins to shift. As temperatures rise slightly during the day, small amounts of ice may soften at the surface, creating a subtle change in the balance between solid and liquid water. This change does not yet reach the frog's position, but it marks the beginning of a broader transition. Over time, these small adjustments contribute to the conditions that will eventually allow thawing to occur. While the wood frog remains frozen, other animals begin to respond more actively to these early signals. A ground squirrel, deep within its burrow, may begin to adjust its internal cycles slightly, preparing for the eventual return to activity. A bat within a cave may experience small changes in temperature that influence its state. A bear, still within its den, may begin to show subtle increases in internal activity as conditions shift. These responses remain minimal, but they reflect the influence of the changing environment. The wood frog, however, stays steady during this early phase. Its frozen state continues, supported by the stability that has been maintained throughout the winter. The internal balance of ice, water, and protective compounds remains intact. The frog does not respond immediately to these external signals, as its survival depends on maintaining its current condition until the environment provides the right conditions for change. The repetition of these small environmental shifts creates a gradual transition rather than a sudden event. Each day brings slightly longer periods of warmth and light, followed by cooling at night. This pattern allows the environment to move steadily toward a new state, without disrupting the frozen condition too quickly. The frog remains within this steady progression, unaffected by the minor fluctuations that occur at the surface. The importance of this gradual change lies in its ability to protect the frog during the transition. Sudden warming could cause uneven thawing, which might affect the balance within its body. By allowing the environment to change slowly, the conditions for thawing are established in a controlled way. This supports the frog's ability to move safely from its frozen state back to activity. As time continues, the signals become more consistent. Daytime temperatures remain slightly higher for longer periods, and the intensity of sunlight increases. These changes begin to extend deeper into the environment, gradually affecting the layers beneath the surface. The frog remains frozen, but the conditions around it are moving toward the point where change will begin. Other animals continue to adjust as these signals strengthen. A ground squirrel may begin to increase its internal activity in preparation for emergence. A bat may shift more frequently within its environment as conditions change. A bear may begin to move within its den, responding to the gradual increase in warmth. These changes remain controlled, reflecting the slow nature of the seasonal transition. The wood frog's position within this process highlights its reliance on environmental timing. It does not respond to the earliest signals of change, but instead depends on the accumulation of these signals over time. Only when the environment reaches the right balance will the conditions allow its frozen state to begin reversing. Until that point, stability remains essential. As early spring keeps develop, the environment moves closer to this threshold. The ground begins to warm more consistently, and the insulating layer of snow gradually decreases. These changes are still subtle, but they build toward a moment where the frozen state can no longer be maintained. The frog remains preserved, but the conditions supporting that preservation are slowly shifting. Through this gradual process, the environment prepares for the transition that will follow. The wood frog remains still, held within the balance that has supported it through the winter. Around it, the world begins to change, moving toward conditions that will allow movement and activity to return. This stage marks the beginning of that shift, where stability gives way to the possibility of change. As the frozen state passes and the wood frog fully returns to activity, the environment around it begins to change in a more visible way. The ice that once held its body in place has melted, and the ground softens as temperatures rise. Water moves more freely through the soil, and the stillness that defined the winter months begins to give way to movement. The frog, now active once again, responds to these changes as part of the same cycle that guided its survival through the cold. At first, its movements are slow and controlled. After a long period without activity, its body adjusts gradually to the demands of motion. Muscles regain coordination, and balance returns as the frog begins to move through its surroundings. This transition is steady, allowing its systems to operate together without strain. Each movement reflects the careful return of function following the period of suspension. As activity increases, the frog begins to interact with its environment once again. It moves across the damp ground, responding to the presence of water and the changing conditions. The same environment that once supported its frozen state now supports its return to life. Moisture within the soil and the availability of water provide the conditions needed for movement and activity. Energy use also changes during this phase. The frog begins to rely on its internal systems in a more active way, using energy to support movement and function. This shift marks a clear transition from preservation to activity. The body that once required almost no energy to maintain its condition now resumes the processes needed for daily life. Other animals also begin to emerge from their winter states. A ground squirrel leaves its burrow, its body returning to a higher level of activity. A bat becomes more active within its environment, adjusting to the warmer conditions. A bear emerges from its den, moving into a landscape where food is once again available. Each of these animals reflects the broader shift taking place across the environment. The wood frog remains closely connected to these changes. Its activity aligns with the conditions around it, responding to the availability of water and the presence of suitable habitat. The same internal systems that guided its survival through freezing now support its return to active life. This continuity ensures that the transition holds steady and controlled. As the environment continues to warm, the frog's activity becomes more consistent. Movement becomes easier, and its behavior reflects a return to normal patterns. The stillness of winter is replaced by steady motion, and the conditions that once required preservation now support ongoing function. This shift marks the completion of one phase of the cycle and the beginning of another. The recovery of the frog's body highlights the effectiveness of its adaptation. It has moved from a state of suspended activity back to full function without disruption. This transition reflects the precision of the processes that guided each stage, from preparation to freezing to recovery. The environment and the body have worked together to support survival and renewal. As more time passes, the environment becomes increasingly active. Water flows more freely, temperatures stabilize at higher levels, and the landscape supports a wide range of activity. The frog continues to move within this environment, fully restored and aligned with the conditions around it. This return to activity completes the transition from the stillness of winter to the movement of early spring. Through this phase, the wood frog demonstrates how life can resume after enduring extreme conditions. Its return to activity is not sudden or chaotic, but steady and controlled. Each system functions together, supporting movement, balance, and interaction with the environment. This coordination reflects the same precision that allowed it to survive the cold. As the cycle continues, the frog remains an active part of its environment. The conditions that once required it to freeze have passed, and its body has adapted once again to match the world around it. This ongoing connection between the body and the environment defines how it moves through each season, responding to change with balance and control. As the environment settles into the steady conditions of spring, the cycle that carried the wood frog through the winter reaches a quiet resolution. The frozen state has passed, and the processes that once slowed to a near stop now support full activity. The frog moves within an environment that no longer demands extreme adaptation, yet the effects of that adaptation remain present in the way its body has responded to change. The cycle of survival is not defined by a single moment, but by the connection between each stage. Preparation, freezing, preservation, and recovery are all part of a continuous process that allows life to persist through changing conditions. The wood frog moves through each of these stages with precision, guided by internal systems and environmental signals that remain closely aligned. Other animals follow their own versions of this cycle. A bear that once rested within its den now moves through its environment, supported by the energy it conserved during winter. A ground squirrel that remained within its burrow resumes its activity above the surface. A bat that spent months within a cave now responds to the warmer conditions outside. Each of these animals reflects a different approach to the same seasonal challenge. The wood frog's path remains one of the most distinct. By allowing its body to freeze and later return to activity, it demonstrates how life can adapt to conditions that move beyond what is typically survivable. Its ability to pause and then resume function highlights the balance between preservation and activity that defines its survival strategy. This balance depends on the relationship between the body and the environment. The frog does not act independently of its surroundings. Instead, it responds to changes in temperature, light, and moisture with adjustments that maintain stability. These responses allow it to move between states of activity and suspension without losing function. As the season continues, the environment provides the conditions needed for growth and movement. The stillness of winter gives way to a landscape that supports activity across many forms of life. The frog remains part of this environment, fully restored and responsive to the conditions around it. Its survival through the winter becomes part of the larger pattern of seasonal change. The quiet nature of this process reflects how survival often depends on steady and controlled transitions rather than sudden change. Each stage of the cycle builds on the one before it, creating a sequence that allows life to persist over time. The wood frog's journey through freezing and recovery is one example of how this pattern unfolds. Through this cycle, the connection between stability and change becomes clear. The frog holds steady during the frozen state, then transitions back to activity as conditions allow. This movement between stillness and motion defines how it responds to the environment. The ability to maintain balance through both phases supports its survival. Other animals demonstrate similar patterns, though their methods differ. Each species aligns its internal systems with the environment in a way that allows it to endure the cold and return to activity when conditions improve. These variations show how life adapts to the same challenge in different ways. As the cycle continues beyond this moment, the frog remains part of an environment that will change again over time. The conditions of spring will eventually give way to other seasonal shifts, and the process will begin again. The patterns established during this cycle will guide the frog's response to future changes. The wood frog's survival through the deep cold shows how life can persist through adaptation and alignment with the environment. By responding to change with precision and balance, it moves through each stage of the cycle without disruption. This process reflects a quiet form of endurance that allows life to continue even under extreme conditions. As the environment remains calm and steady, the frog continues its activity, fully returned from the frozen state that once defined its existence. The cycle has completed, and the balance between the body and the environment remains in place. This quiet resolution reflects the continuity of life as it moves through each season. As the season keeps settle into steady warmth, the environment becomes fully active once again. The wood frog moves easily through the damp ground, its body now fully restored after the long period of freezing. The stillness that once defined its existence has been replaced by consistent movement, supported by conditions that allow it to remain active. This change reflects the completion of the transition from winter to spring, where preservation gives way to function. Around the frog, other animals complete their own return to activity. A ground squirrel moves above the surface after spending extended time within its burrow, its body now fully adjusted to the warmer conditions. A bat, no longer confined to the stable air of its cave, moves into the open environment as temperatures support its activity. A bear, having left its den, travels through the landscape, relying on the energy it conserved during the winter months. Each of these animals reflects a different path through the same seasonal cycle. The connection between these animals becomes more visible as the environment supports them all at once. The frog moves through areas where moisture has returned, while the ground squirrel navigates the surface with renewed activity. The bat responds to the open air, and the bear moves through a landscape where resources are once again available. These actions occur together, forming a complete picture of recovery across the environment. Each of these animals relied on a different strategy to survive the cold. The wood frog allowed its body to freeze and later returned to activity. The bear reduced its movement and relied on stored energy. The ground squirrel lowered its body temperature and cycled through reduced states. The bat adjusted to a stable environment while conserving energy. These differences highlight how survival can take many forms, even within the same conditions. Despite these differences, the outcome remains the same. Each animal has moved through the cycle of winter and returned to a state of activity. The methods vary, but the connection between preparation, endurance, and recovery remains consistent. This shared pattern reflects how life adapts to seasonal change, aligning internal systems with the environment. As the environment keeps stabilized, the balance between these animals and their surroundings becomes steady once again. Movement replaces stillness, and energy use returns to normal levels. The frog, now active, no longer depends on preservation, but on the same processes that support everyday life. This shift marks the completion of the cycle that began with the approach of winter. The presence of multiple animals within the same environment reinforces the idea that survival is not defined by a single approach. Each species follows a path shaped by its biology, yet all respond to the same external conditions. The frog, the ground squirrel, the bat, and the bear each demonstrate how different strategies can lead to the same result. As time continues, this cycle will repeat. Conditions will change again, and the environment will once more move toward colder temperatures. When that time comes, the same processes will guide each animal through preparation, survival, and recovery. The patterns established in this cycle will continue, allowing life to persist through ongoing change. The wood frog's journey remains one of the most distinct within this larger pattern. Its ability to move from activity to freezing and back again reflects a precise alignment between its body and the environment. This alignment allows it to survive conditions that would otherwise prevent life from continuing. It is one example within a broader system where each animal plays a role. Through this shared environment, the cycle of survival becomes clear. Each stage supports the next, creating a continuous process that allows life to endure across changing conditions. The frog's return to activity, alongside the movement of other animals, reflects the completion of this cycle and the beginning of another. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about how animals survive the deep cold.